Hello, welcome back to our tutorial series on the voltage regulator, specifically the linear voltage regulator. And in that category, what you have on the screen is a shunt voltage regulator. And we have seen before a complete analysis of this circuit where we wrote the expression of the output voltage, which was VO is equal to VZ plus VBE. And we have seen with the analytical expression how this output voltage VO across this load is maintained constant irrespective of the variations in the load or the variations in the input side. So please refer back to that video in this series on our YouTube channel. And if you haven't yet subscribed to the channel, do so for more technically rich and informative content. So we'll continue now in this session, the simulation part. We have this spice circuit simulator and you can see the circuit is ready. What you have here is a zener diode, and beside that you have a transistor. So and there is a resistor right here R1 which has a value of 1k, and let's say the input unregulated voltage source is about 15 volt, and we have chosen the zener diode which has a breakdown voltage of 6.2 volt. It is from the manufacturer on semiconductor. The diode part number is BZX dash dash. So this was done. So IZ and VZ are the specs of this diode that you can refer from the data sheet. It has a maximum current that it can handle and all that. Similarly, right click on the transistor. You see this is the transistor which is 2N2222 from NXP Semiconductor. It is a NPN transistor, as you can see from the arrow coming out of the emitter. That's the direction of the current. It has a maximum voltage drop handling capacity across its collector to emitter, which is collector to emitter open circuit voltage of about 30 volt. And the maximum collector current it can handle is 0.8 ampere, which is 800 milliampere. Load is a 10K, across which the output is developed, and it will. So now we want to understand the operating point of this circuit. It means once we switch on this voltage and all parts are connected, we want to see the various voltages and the currents in the circuit and whether the VZ plus VBE. So VZ is 6.2 volt plus VBE of this silicon diode is about 0.7. So 6.9 volt total should appear at the output. So want to do that, and we'll also monitor what is the value of diode current, collector current, load current, etc. So before that, what about we just right click on the net and we highlight the net. So this is a common net. Again, right click and we want to label it. So this is an output net. So we'll just say this is my VO port is output. I will click OK and I place that. Then I press escape button on my keypad to get rid of the symbol. Then I go to wire. I want a wire. So right here, I select the wire and connect the output port to the circuit. Similarly, this net, I highlight, I right click here, I label it, and I want to say this is my input. So let's say VI or VIN. This is an input port, okay. And I see that I can actually place it here. And again, I will press the space bar, space on the keyboard, space keypad, so I can get the full schematic on the screen. Again, I click wire and then connect this right here. Now, after that, I can have some other node. For example, if I highlight this, this is the same node and this is the same net again. So, and this is the ground net. So which one I can do more? For example, if I want to label this net, maybe I can do that, but it's fine. Now I click simulate, go to edit simulation command. Now so many analysis, I select DC operating point. So this analysis, a syntax of which is .op it stands for operating point. I click OK and I place it on the screen. Again, I press the space button on the keyboard to adjust the schematic on the screen and get all things visible on the screen. Now I'm done, and let me compute and simulate the operating point of this circuit. So go to simulate and click run. Now you can see here all voltages and the currents are there. So first voltage is V in, voltage at the node V in, at the port V in, which is 15 volt. Output voltage is 6.652. So remember the zener diode has a drop of 6.2 and the VB was about VB. We want to understand how much is the VB. What about we just let's say just this node, we just label it. For example, this is not input, not output, so we'll keep it like node A. Okay, or it's the base of the transistor. So you just type base and click here and we'll just say base. Okay, so now if you right click and highlight it, it will be net labeled as base, and this is your emitter. Now again run the analysis. So this is base. Now you see input voltage is 15 volt, output voltage is 6.65, and the voltage at the base is 0.7 volt. All right, so you can actually check that the zener diode breakdown is 6.2, and plus the voltage at this at the node B with respect to ground is 0.7. So essentially it is about 7 point something, 7.2 volt should be your output. Then why we are getting 6.65? That is the question. Okay, let us analyze that. So to circumvent this issue, I think we have to change the value of R1 because the output is not what is expected. So we right click and let's say it is 100 ohm, for example, so that we let the large current flow through the R1 and the diode, and then to the base of the transistor. Subsequently, the beta of the transistor will multiply the base current, and the IC will then be increased so that the collector current and the load current all will be adjusted. So let's run the analysis, and now you see 6.2 volt is the zener diode drop plus 0.7 is the VB junction drop. That equals to VZ plus VB is about 6.9 volt approximately. Makes sense. Your VB voltage, base to emitter voltage, is 0.79 volt. The collector current is your 0.079. So it's about 0.79 milliampere. IB is your 468 microampere, and then the emitter current is again 79 milliampere, and the diode current is again your 468 microampere, and the current through the R1 is your 80 milliampere. Current through R2, which is the load, is your 693 microampere or 0.693 microampere. And that's the current being given. So we see that the operating point and analysis of this transistor. Okay, and all those things. Okay, so that's all. We have seen all these voltages and the currents into the circuit, and our output is now 6.65 volt, is a constant voltage. The voltage at the base emitter junction is 0.7. Collector current is 7.6 milliampere. The base current is 36 microampere. Emitter current is again 7.6 milliampere, and approximately the current through the diode is 36 microampere. The base current and the current through the diode are same, and the current through R1, which is the total current being supplied to the circuit, is this one, so which is about 8.3 milliampere. So we see that the current through the diode is 36 microampere, and current through R2 finally is 0.6 milliampere. So all these parameters gave us information about all voltages and the current. Now, what if we want to see if there is a variation in the load or the variation in the input? If this voltage, which is 6.7, was it 6.7? Yeah, 6.65, how it is maintained. Back to our circuit, and did we see the analysis? We'll just write that again. So here, the parenthesis X, and now we'll write the spice directive dot step param X from 10K to go to 15K at the interval of 0.5K, and I want to see how this will sweep. So I keep it here and I run the analysis like .op. That is the analysis. So it's done. See, and now I want to check the output of this circuit. So you actually can see that this is about varying from 10 volt DC. 10, no, 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 I made a mistake here. No. Okay, so we are back here. So we see now we have wrote this command dot step parameter, and we are sweeping this value of the load R2 from 10K to 15 volts. So I'll run the simulation, and I'm with this window, and I see the red probe on the schematic. I click, and the output voltage is varying from 6.65 volts. See the y-axis here, to 6.655 6.6528 to 6.655. There's a very less variations. You can see that it's almost constant. Zoom to fit. Not much variations is there. So it's pretty robust variation I'm getting. Next, what if I want to just, let's say, keep the value of load constant, and instead I would vary the input voltage. So for that, I will just remove this step analysis, .op analysis as well, and go to simulate, edit simulation card, and then I'll do the DC sweep. So I want to sweep the DC voltage source, name of which is V1. Don't get confused between V1 and V in. V in, remember, is a net name, and the name of the voltage source is V1. So you have to do that. So use type of with linear. Let's say it is 15, and I want to go up to 25, increment of 1 volt, and we'll see. Once that command is ready, place it on the screen and then run. Now here you got this, and look, your output varies from 6.651 up to 6.741. So this much variations you will have in the output. So it's there is a change from about 100 millivolt. So whether or not it is acceptable to you depends on the design. So similarly, try varying all these parameters into the circuit, like changing the value of R1 or R2 or voltage source V1, and you will have different results. So we saw in this one how this output is maintained irrespective of the variations in the load or in the variations in the input. Similarly, you can plot how the load current pair vary. You see the red arrow in the schematic. I just click and it is going to plot me the IR2. So what I'll do on the waveform window, I'll click on the output voltage and delete this stress. So on the window, I have this blue curve, which is IR2. You see the label is there. And this shows me how the current is varying. Similarly, I want to plot any current, let's say the collector current. So here I am going to plot the ICQ, and ICQ is given. So I can use the add plot plane and take the ICQ up. So it shows the variation from 7 milliampere to 18 milliampere, all that variation. Similarly, I can go to screen, see the base current. Base current is in the red. I click that. Similarly, emitter current and current through the diode. The direction of arrow shows it from anode to cathode. So I just click that. So ID1. Again, I right click on the waveform window, add plot pen, and ID1 I take up. So ID1 is in the pink, 35 microampere to 90 micro. So this is how you do all this analysis. So hope you like this video. If you did so, like it, comment on it, and share with others for wider reach. Till then, wish you happy learning, and subscribe to the channel and stay tuned. Thank you.